right? So UDP53, DNS, domain name service. So as the word says, the job of this protocol is to resolve a domain name into an IP address. Now there is nothing more to focus on this one because it's not going to PhD. But one thing I want to tell you, in addition to what people know about DNS, is even with the help of DNS, you can prevent attacks. Even using this feature. So DNS is very important for anyone to go online. Without DNS, it's not possible for a computer to know the IP address of the web servers. So um, there is a feature called umbrella. It's not Ccna, so don't. But you can, if you are interested, you can Google. There's a feature called Cisco's umbrella. What Cisco's umbrella will do, it will it will first check whether the domain that people are trying to go is a good domain. It's a good website. Is it under a good category? That is what it will check first. It will check, and then if the website that I'm trying to go is under the category of good, only then it will give the IP address of the domain to me. Otherwise, it won't give me. So, how many times the user types www.arcud.com, arcud.com, no page will appear. Because Arcud is found as a bad website for the umbrella. So your request, when your DNS 53 request trying to go out from your network, umbrella will say, wait a minute, let me first check. Let me first check whether it is in a good category. Then umbrella will say, no, this is not a good website to go. So don't resolve DNS. So DNS reply will not come to computer, and my computer will not know from which and to get the web page. So it's a very good idea to prevent attacks or to avoid going to an unwanted website from where malware, spyware, viruses may come and affect our network. Okay, so next is ARP, Address Resolution Protocol. Uh, this is to resolve an IP address into MAC address. Whether you are doing layer 2 communication or layer 3 communication, MAC address is must. Very important, the MAC address. Without MAC address, no routing possible. Also, without MAC address, no switching is possible. So routing depends on MAC address. How? We have covered the OSA layer, right? The OSA layer, if you notice, in network layer we have source and destination IP. And in the data link layer we have source and destination IP. Now, when I am pinging from this computer, which is connected through a switch, 10.0.0.1, 10.0.0.2, 10.0.0.3. When I ping from A to B, I ping from A to B, the source, my own address, I know very well, 10.0.0.1, and the destination, I'm pinging B, so B's address I'll put in this computer saying 10.0.0.2. From my ping, A knows that you're trying to go to destination 10.0.0.2. and then let's say the MAC address of minus A, but the MAC address of B is unknown. While pinging, we don't mention the MAC address. First of all, we will not know the MAC address as a user. User will not know the MAC. So the packet is not complete. When something is missing, the OSI encapsulation fails. The packet cannot leave the computer. Now, ARP comes into picture. ARP sends a layer 2 broadcast, and the layer 2 broadcast will have a payload. Its data carrying who is 10002. But the packet is sent as a broadcast. It's a layer 2 broadcast. So here it is going to be FF 12 times. MAC address is 48-bit size, right? MAC address is 48-bit size. So 4-bit of binary is 1 bit of hexa, which means there will be 12 hexabits for a MAC address. And the biggest number, no, that's not correct. That's not right. Where you learned it, that's not right. It is not always. Some device will do the gratitude art, it's called gratitude art. But again, I'm telling you, it will go only up to switch. How will A know about B if B is sending its MAC address to switch? Repeating again. How will A know about the MAC address of B when you connect B to the switch? Only switch will know the MAC address, not the other computers. Okay, but that is also not all the time. That also I want to repeatedly say here. Not all the time. The gratitude ARP is not all the time. That depends on the vendor. That depends on whether the line protocol will go. Now, that is not going to solve the ARP issue here. ARP have to go to the dead end, means the destination, to know the MAC address. Switch, even if switch knows the MAC address of the computer B, switch is not going to say, okay, I'll give you the answer to your ARP. Take this is the MAC address. No, switch is not going to do that. Switch will not do proxy. So when A sends a layer to broadcast, when A sends a layer to broadcast, the broadcast goes to everyone. Again, I'm repeating, A sends a layer to broadcast. When switch receives a packet with a destination of a broadcast address, it must forward the packet to everyone. It must, it should, it will forward. Now you said switch knows about B, now why it is sending forward, why it is forwarding to all. Switch is forwarding to all because the destination of the packet is a broadcast packet, a broadcast address. So switch is not going to see deep into the packet and know that this is an ARP packet. So he is looking for MAC address 10.0.0.2. Let me help. No, that's not switch job. Switch will not know whether it is an ARP packet or a ping ICMP packet. It will simply check the destination MAC address of the packet, and the switch will forward it to all the ports connected device. So it goes to all the devices. Now, the packet that went to C will be dropped. Why? When C takes the packet and process it, in the payload it is said, who is 10002? This is not 10002. So C will say this is not for me, so it will drop it. But B will respond saying, yes, it's me, my source MAC address is B. Uh, request was coming from A, so my destination MAC address is A now. And in the payload, it will say for 10002, MAC address to be used as B. Now, this is going to go, so alright, this is layer 2, layer 3 information and the payload. The R payload, R reply we call it as. So when this packet approaches the switch checks the destination and it does a one-to-one mapping, not flagging. For the ARP reply, it knows to whom to reply. Knows the destination is not FF. But ARP request was a 12 time F, which is later brought. So this is how ARP learns the IP address, sorry, MAC address for the IP address that you want to go. After which, the ARP reply, it's got updated into the ARP table in computer B, in computer A. Computer A maintains an ARP table in which it will have 10002 MAC address as B. So now when the ICMP, when you ping, the ICMP protocol will go to the ARP table and take the MAC address, puts it here, boom, it sends the packet out. So this is how the ARP resolves. Now let us say we got a router and we got a destination 20002. Okay, now this router, let's say router A, will have a routing table on F00. The connector network is 10, and F01, the connector network is 20. We call this as routing table. Now, let's see how ARP works here. We are going to ping 20.0.0. So when you're pinging different network, meaning my local network is 10, and the destination to which I'm pinging is 20, not the same network. So what the computer will do, what this PC will do is it will look for the gateway. So you should configure the gateway address. What is gateway? The router's address is the gateway. Is it right? Yeah. So this address will become the gateway address for this all computers. So the operating system, it may be Linux or Unix or Windows, this is how they are designed. They automatically take the gateway as the destination, and it will send the ARP request. I understand. It will first see the IP address of the ICMP packet, the thing here that you are doing, will never change. But the ARP request is going from A to B. Sorry, A to this router. It sends the ARP request asking who is 10004. Same like B was responding, now the router will respond with the MAC address. Let's say the MAC address here is DDD, and the MAC address here is EEE. and here it is FFF. Right. So what happens is it sends an ARP request to the gateway address, and DDD is learned. And you see the packet's destination IP address never changes. Even though the current destination is 10.0.0.4, but the IP address of the destination is still 20.0.0.2. You understand? So it is this MAC address that helps to move the packet from this to the intermediate destination, which is the router. After going to the router will only look into the, see, when a packet is received, router will definitely look into the MAC address to check whether the packet belongs to me. Yeah, packet belongs to me. My MAC address is DDD. So with the ownership, now router A has got ownership. Yeah, this is for me. My MAC address. See, so I'm eligible to open the packet further. So it opens the packet further, and when it finds the destination as 20, what it has, it checks the routing table. Okay, routing table says 20 F01. I have to push via F01. So what it does now, it changes. Source IP will be same. Destination IP is 20. And then source MAC address is EEE. Now from here it is going to send out. And destination MAC address, I don't know. It don't know the MAC address of 20.0.0.2. Router A also will maintain an ARP table. Some people think that ARP is only layer 2. It will not be there in the router. No, that's their imagination. No, router A will send an ARP request asking who is 20.0.0.2, and ARP reply will come saying it is FFF. So for 20.0.0.2, FF. So using this ARP, it puts FFF and sends to the switch, and switch forwards it to the final destination. So here 2 times ARP you can see. If you have one router in the middle, there are 2 times. So two times ARP. So no, it will have ARP table. That is how we can call it as MAC table. ARP table, the layer 2 forwarding table. There is no need to see MAC table will have a VLAN number. That is very important for a MAC table. But where is VLAN in router? So there is no need for a MAC table. MAC table will have VLAN number followed by the MAC address followed by the port number. Port number. That's all. So these things are not necessary because I know the port number to which port via which I need to send the packet out from the routing table. Routing table shows you need to go via F01, and then what? ARP table shows the MAC address of the destination. So there is no need for a separate MAC table for router. But if it is a multi-layer switch, if it is a distribution switch, it will maintain both MAC table, routing table, ARP table, all together, because it's both layer 2 and layer 3 table device. So layer 2 device will have a MAC table. Layer 2 device will have MAC table. Here also we will have MAC address in the table, but we don't call it as MAC table. It is called as a forwarding adjacency table. Adjacency table. Because there is no VLAN. Alright, so we have done DNS, we have done ARP. Next, what we'll do is we will we'll get into IP address. IP, first of all, the protocol IP, Internet Protocol. Internet Protocol. Even before IP, there was a network. There was there was a protocol. Instead of IP, there was another connectionless CLNS, 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 connectionless network service. So that was using different type of number to identify a device. So IP is not the protocol in the internet. There is many. Apple Talk. Apple Talk is another protocol like IP. Um, so there were many earlier, but they all lost their value because of this IP. So this because this IP is more easy to use. So how this IP protocol works? IP protocol works by using just 32-bit number to identify a device. IP protocol uses a 32-bit value to identify a device. So the protocol's job, IP protocol's job is to identify the right destination. And to identify the destination, it uses 32-bit address. So IP address is what we call it as address, IP address. So the IP protocol uses this address. And this address is only 32-bit binary size. Thirty-two-bit binary IP address is 32-bit binary address. Fine. Now this 32-bit binary address, because it is binary, it is not user friendly. So what they decided to do is they decided to convert this into decimal and give it to us. Fine, that is one thing. Secondly, they don't want to keep this 32-bit in one um, cluster. They want to make it classify into multiple size. Based on the size, they want to classify the address, and that's what we call as class A, class B. Depending on the size of the network, we will pick one of this class. For those who need large amount of IP address, like in lakhs, 1 lakh, 2 lakh, for them class A. And for those who need like 50,000, 40,000, class B. A small number like 100, 200 computers, then class C. So, so that we will not be wasting the IP address. So if someone needs only small amount of IP address, them only that much. I need to give an IP address which will, or a subnet which will provide lakhs of IP addresses. So, like when people who in the job of distributing food, they give small amount to children and big amount to big people. It's likewise, they don't want to waste. Likewise, the classification is done, and this is how it is divided. Study a bit for our easy, uh, in order to handle this IP address very easily. It is divided into 4 octets by using 3 dots. 4 octets. So, as we know, octet is 8-bit. So 8 multiplied into 4 is 32. So you got 32 bits into four groups, broken into four small groups called octet, in which the first octet is network if it is class A, and more bit is given for host. More bit. How many bit? 8 plus 8 plus 8, 24. So 24, 2 to the power of 24 addresses can be derived from every single class A address. Every single class A address, meaning class A is ranging from 1 to 126. If you take just one, you can have 2 to the power of 24 IPRs. And if you take the second number 2, in 2 also you will have these many IPRs. Likewise, you will go up to 126. 126 multiplied by 2 to the power of 24 is the total number of IP class A. Yeah, you understood, no? All right. Now, number of IP address in each network. This is what network 1 to 126. In each network of class A is 2 to the power of 24, I say. But actually, it's 2 to the power of 24 minus 2. The reason is the first number will be a network. You cannot use it. And then the last number will be a broadcast. That also you should not use. So when you detect this broadcast and the network address, we put minus 2. Right, it's 2 to the power of 24 minus 2. That's the address, number of address that we'll get for each segment. Sorry, each network. Now, likewise, class B, likewise in class B, we got network, network, host, 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 host. So in here, if you see, the number of bits for host is reduced. 2 to the power of 16 minus 2. But the network is more now. You see here also you have bits, here also you have bits. And if you see here, it stops at 126 and 127 is dedicated for loopback. We'll talk about that later. So now 128 to 191 is what class B range. For example, 128.0 is one network. 128 dot this socket 1. 128.2 goes like that. And then when it reaches 128.255, it goes to 129.0. See? Likewise, it can go up to 191. This becomes what? Keep growing like 130, 191.255. So you will have a big amount of networks, very big amount of network. Whereas here, the total number of networks itself is only 126. Total number is here only 126. Okay, now here we say 2 to the power of 16. The reason is 16 bit only for the host. All right, next. Class C, if you take, Exactly. And then this is first. And the range is like 192 to 223. And the number of IP addresses is 2 to the power of 8 minus 2. So if you see here, somewhere around 254 addresses will come here for each network. Here somewhere around 65534 addresses. Here some lakhs of addresses you get for each subnet. So depending on the user's need, one of the subnet from this class, one of this class will be given. Now, why is this number 1 to 126? Why not 1 to 130 or 150, a round number? Why it is starting with 192? Why not 190 or 200? Easy to remember. Why it stops in 223? Why can't it be 225? Any answer from your side? So, how did they derive this range? Is what we are going to see. There is a logic behind this derivation. What they did is, in order to get this classes, this is what they did. In the first octet of all three classes, class A, class B, class C. The first octet you see 0, 0, 0, 0, 0, 0, 0, 8 bits. The first octet, they made it as 1 here. So, no, 1 here. The first octet, the first 2 bits, this is made as 1 and this is made as 0. Now, when all these are 0, hold on please. I think I'm confusing myself. Yeah, 1 only here. This is 1 here and this is 0. Now, the minimum is 0, no? So we begin with 1. The smallest number you will get out of this is only 1. So the biggest number is making all these bits on. When you make all these bits on, what do you get? This is showing getting 127. 255 minus 64 is what? 190. The first octet is made constant, 0, 0. That will never change. What is the minimum here? The minimum is 1. And so now the minimum number you can have is 1. So putting this one, the first bit on, you get 1. What is the maximum? You on all these things. When you add all this, what do you get? 255 minus. These two bits are 0. 255 minus 192. 255 minus 190 is 63. No, that's not the story. Okay, only this is made constant. Okay, this is the final. This is made constant. And this is constant, meaning this will never change. 1, so this is 1. This is the biggest one. And now you get 127. 255 minus, what is this? 126, no? And now you see, you get 127, isn't it? Is it right or not? Are you sure? Let's try it. So when you make all this 1, yeah, that is 128. So this will be 127. Addition of this will be 127. That's right. That's right. Which is like 64 plus 32 plus 80, 16 plus 8 plus 4 plus 2 plus 1. You get 127. 100% sure. Don't know, no need to calculate. Now, this is how they derived class A. And class B, what they did is they put 1 here and 0 here and they made this as constant. 1 and 0. So, the minimum, even if all these are zeros, it will begin with what? 128, because this is on, correct? Yeah. So here it is not 126. I was trying to add with 126. What is it? So it's 128. Okay, now 128 is the beginning of class B, and yeah, it's actually 256. But because we begin from 0, not from 1, it will be 255. If you count from 0, it will be 255. If you count from 1, then it is 256. Okay, so here the minimum is 128. Did you get the answer? How? Because all are 0, all the bits are 0. And the maximum is, you cannot make this as 1, this should be 0, and only these bits are 1, which is 128 plus these bits are 63, which is 191. Yeah, you understood, no? 191. If you add this, you get 191. And then for class C, what they did is they made these two as constant. So these three as constant. 110. So first it was only 0, and then 10, and then 110. See, there is a logic here. So the smallest is 128 plus 64, which is 192. That's the beginning. You see, which is immediate number. And then the biggest is making all this 1, which is 255 minus 32. 255 minus 32 is 223. Yep. You see, 5 minus 2 is 5 minus 3 is 2, 223. So this is how they derive this range. Just to derive, they made this 0, 1, 0, 1, 1, 0. They got this. In which this class A have sacrificed 127 for some other reason. So class A is not 1 to 127, even though it is coming under class A, which is 127 is coming under class A, but 127 number is given for loop back address. It's not loopback interface, it is called loopback address. Loopback interface is a virtual interface which we'll see later. This is loopback address. Loopback address will always begin with 127. The purpose of this address is to check whether the 7 layers. No, 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 no. Devices reaching you are pinging and you are checking now why you need loopback. When you ping, ICMP packet goes and ICMP reply comes. You have ping, we use ICMP to check the device reachability. This is loopback address type. Address type called loopback. Always begins with 127. Nowhere this address is configured by us. But when you ping you, if you will get reply, only then your device is eligible to be a part of network. For example, you see, I go to my command prompt and ping 127, tell any number. 91.91.91. You see, I'm getting reply. This address is nowhere in my network, but I'm getting reply. Then who is replying? My own driver. My own network driver is replying. My own physical layer is replying. I'm pinging this from this top layer using this application called command prompt. Command prompt. And this application generates this ICMP packet and it is sending to the physical layer. If the physical layer is properly installed, if the physical layer has got the trans receivers, the drivers properly installed, and if the physical layer is active, only then I will get this reply. This is a self-diagnostic test that we run to check whether our computer is eligible to be a part of network. Which means when you get reply like this, your computer is ready for partaking in network communication, right? So if you don't get reply from, if you don't get reply for this address, means you are not able to send and receive. That's the meaning. See, I send the packet to my physical layer, and I receive the packet from my own physical layer. That is why we call this loop back, connecting back myself. Connecting back myself to check whether my device is sending and receiving. Yes, I can see my device is sending the packet and it can receive the packet. It sends the packet to the physical layer and physical layer responds me. I receive the packet in this application as a ping reply, which tells that my device is ready for internet communication. If you don't get replies like this, if you don't get replies like this, you need to troubleshoot your own laptop instead of calling the ISP, telling that they have an internet problem. Instead of reporting, instead of complaining, you first you need to check your own computer. When you get the reply like this, your computer don't have a problem. There's a problem in the ISP side. ISP might have not given DHCP IP address for your laptop, or ISP may have some problem in the path, some loose connection, disconnection, something like that. So it's not our problem when you get the reply. When you don't get reply, the problem is not outside, it's in our laptop. So it helps to try it out. Yeah, NICART driver or your Wi-Fi card driver. Fine, that's the purpose of loopback 127 dot any number alpha alpha alpha. It can be any number is loopback. Actually, they have wasted a lot of address. For this purpose, if you have at least just one number, 127.001, this itself is more than enough. But you see, they have wasted the entire 24-bit. Those days, no purpose. That's literally design defect. They did not realize that we are wasting. So in IPv6, they realized it. In IPv6, if you just put ping colon colon 1, this is what IPv6 loopback will say. Let me show you. Ping colon colon 1. Just one address. See, you're getting reply from. There is no other loopback address in IPv6. Just one. Whereas in IPv4, they have wasted um, almost 1 lakh plus IP addresses, almost 2 lakhs of IP addresses wasted. Now you cannot change it because it's as per the standard. They made it standard IPv4. IPv4 standard. Okay, so now we learned the range of class A, B, and C, and we learned how the range is derived, and then we learned the loopback. There is one more address which is in class B you cannot use. So you cannot you cannot assign any device with an IP address starting with 127. Yeah, you should not assign. If you try assigning, it won't take it. It will say this is a loopback address. It's not assigned. You try assigning later, it will throw error. Secondly, you cannot assign an address in class B. There is one address which is so that address we call it as APIPA address, automatic protocol, APIPA, automatic private internet protocol address, APIPA address. This address is from class B. As it is said, it is automatic and a private IP address. A private IP address which is going to come automatically to your computer, not from a DHCP, but it is still automatic. Then who is giving this address? Your own operating system. Your own operating system will generate an address. And this address is to tell that DHCP is not giving IP address. It is complaining you. When you see APIPA address in your command line, when you type ipconfig, instead of seeing an IP address, if you see an APIPA address, it will look like an IP address, so you should not be misguided. So if you find an APIPA address, then it is simply telling that I waited for DHCP to give IP address, it didn't give. So I'm automatically generating this private IP address simply to tell you that DHCP has got some problem. Yeah. So that address is just to tell you the message that DHCP is not giving. And that address will not be, APIPA address will not be used for communication. Got it? Right. So 169 is class B address. 169.254. This is the address, this is the number with which an address will be generated. Again, this address will not be used for communication. Every computer will start throwing this address if someone turns off the DHCP server. Your device is supposed to get IP address from DHCP server, but because the DHCP server is off, the devices, the clients, the DHCP clients, your laptops, your computers, they wait, and when the timeout happens, they automatically generate this address 169.254. So when you check your IP address in the computer, when you check an IP address in your computer, and if you find 169.254, you can immediately call the ISP saying, "Hey ISP, see, I'm not getting an IP address. I'm getting a PIP address," which means I'm not getting address from a DHCP server. Right. This helps to decide where the problem. You understand? So this is class B range, which is not eligible to be an IP address, so you cannot assign it. Likewise, 127 beginning with 127 also should not be assigned. These two are for purpose. Loopback is one purpose to check whether the layers are working fine, the drivers are proper. Apipa is to tell that DHCP is supposed to give address, but DHCP is not giving. So we'll stop